So even functions are symmetric over the y-axis. They're Grasser. Odd functions satisfy that when you make the input negative, the output becomes negative. So we saw graphically some examples of even and odd functions. Let's just verify those same examples now analytically. Let's just check that they satisfy these equations. So let's do that. And I think I'll follow the strategy of I do one, then you do one, and then we split things up. So f of x equals x squared plus 1. What are people's intuition? Even or odd? Or neither? Even. Odd. Neither. I feel like more hands should have come up than came out total, but that's okay. Let's go through the check. I think even was the one that had votes, so let's check if it's even. So to do that, we need to see if f of x is the same as f of negative x. There's a formula for f of x. Let's see if we can just simplify down a formula for f of negative x. Sorry, I'm off screen. So let's see if we can take that formula for f of negative x and simplify it down. So what does f of negative x mean? It just means replace the x in that formula with negative x. Negative x, then you square it, then you subtract 1. And this doesn't look obviously like that, or maybe it does. If you want to see if they're the same, maybe we can just simplify and see what happens. What simplification do you see?
Well, everything squared is, you take a negative away, negative.
Awesome, yeah. Because negative x squared means negative x times negative x. The negatives will cancel. All right. Now that we've done that bit of simplification, is that exactly the formula for f of x? Awesome. Being even doesn't necessarily mean that the function isn't odd. There is exactly one function which is both even and odd. And I won't tell you what it is. I'll leave you to meditate on that. But it might be this function. So let's check. If I want to see if this is odd, well, let's plug in a negative x for the x, so negative x squared minus 1. Then I want to make all of that negative. So maybe some color coding is in line. This negative sign is that negative sign. This negative sign is that negative sign. All right. That look like something you can simplify? What things would you want to do to simplify?
Distribute the negative.
Let's distribute the outside negative. So let's see, that would become negative x squared minus negative 1, so plus 1. All right, what next? Well, I can do the same thing as I did in the previous line, right? Negative x squared with parentheses appropriate. That negative goes away. Equals, so this negative sticks around, negative x squared plus 1. Is that the same formula as for f of x? So this function is not odd. There's a function that is even but not odd. And let's just see these last couple. G of x equals x cubed minus x, h of x equals x cubed minus 1. So take a look at g of x. Many people think, by looking at that their intuition is that that might be odd. How many people have the intuition that that might be even? Cool, so I think the odds have it. People think they could go through the walk of checking that if this thing is odd. Would people like me to say once instead of being quiet? Cool. Then, start here. And you can absolutely discuss with each other at any point during this process. if you want to move to get closer to someone to talk to them, go for it. Alright, well maybe let's hear it. Do people have a conclusion between even or odd? Is it even? Is it odd? Cool. Shall we go through the walk of checking that it is actually odd? Yeah, cool. See some heads nod, let's do it. So, apparently if it's odd, the negative g of negative x should just become g of x. Let's see if that happens. So, I'll add in the color coding. So, all of it's made negative, so I need negative sign around absolutely everything. Next, I need to plug a negative in for x, so that will be the color's not good enough. Negative x squared. Thank you, that would change things, wouldn't it? Minus negative x. All right, did I successfully replace all the x's with negative x's and then stick a negative sign out front? All right, now we gotta simplify. What should we do? Yeah.
First you do inside the parentheses, so you have your negative x cubed is negative ends up being minus x cubed, and then your minus x equals plus x.
Nice. So negative x cubed is negative x times negative x times negative x. So it just becomes negative x cubed plus x. Cool. What next?
Distribute the negative.
Awesome. So that'll become x cubed, because those two will cancel. Negative distributes to this, becomes negative x. Is that exactly the same formula as we started with for g of x? Anyone do the walk of seeing if it's even? What'd you get? Is it even? I see some heads shaking. It turns out, yeah, that's right. Not even. And let's just do one last check. And I might split you up and assign things. So there's a function h of x equals x cubed minus 1. People think it's likely to be even? Anyone think it's likely to be odd? All right. So there were no calls for even, but there were a few calls for odd. I agree, this is not even. Let's check if it's odd. Go through the walk. Yeah.
I'm confused, so that's exactly the same as odd.
Ooh, because this is negative g of negative x that we just computed. If negative function of negative x, so if you make the input negative and then the output negative, if that's the same as the original function, that's what odd means. And maybe that looks slightly different from what we got on the previous page. On the previous page, we said odd means, and you can like pull out the negative sign. So all I've done here is I put all the negatives onto the same side of the equal sign by multiplying that over to the other side. Yeah.
Does it matter which parentheses you do first? Like that, you know how like there's an outer parentheses and then there's the inner parentheses?
As long as you're careful at each step.
Okay.
So like if you distribute, in fact you could do them at the same, in the same step. They're sufficiently independent that I think it could walk out. As people finish this up and they get a resolution, go ahead and compare with those orange here. Just want to see how confident people feel. Cool. So let's just jump to almost to the conclusion. You take negative h of negative x and you simplify it as much as possible. What do you wind up with?
X cubed plus 3, or plus 1, sorry.
And I'm going to put particular emphasis on that plus sign. People agree with that? Anyone want me to go through the walk? All right, is that the same formula as we had for h of x? Nope. So is it odd? Cool. So this is not the same as h of x. So this function is not odd. It's also not even. It's possible for functions to be neither. That feel pretty okay? Nice. So, there's the idea of even and odd functions. Let's talk about something, unless people have questions they want to ask, something that just seems off. Yeah.
So for the f of x, x squared minus 1,
Uh-huh.
is it even or odd?
It is even,
Neither.
it is, this first one,
Yeah.
it worked out to be even.
Okay, but that's not odd, not even? No, that's, wait, no, I was confused, never mind.
Okay.
That's just my fault. I read the not even as the same problem. The
Oh.
orange, sorry.
Okay. I can understand how that would happen. So that last one is neither. This one worked out to be odd. This sucker worked out to be even. Here's a function. It happens to be x cubed minus 4x. And maybe before we do things about the actual topic, intervals of monotonicity. Even, odd, neither, or both. Even? Odd? Neither? Both. I feel like more than like the 4 hands that came up should have gone up. Let's just recall, so those of you who said odd, why? How do you check for oddness using a graph?
You multiply everything by a negative?
Yeah, you multiply everything, meaning the x values and the y values. Yeah.
You say if you like put a point and then flip the paper, if it's the same, then you say it yesterday.
Awesome, yeah, both of these are the same, so let's do both in order. So here's a point that's on the graph. If I make the y value opposite of what it used to be, and then the x value opposite it used to be, it's still a point on the graph. It sure looks odd. The other strategy is pin down the origin, rotate 180 degrees. Is it the exact same graph? Yeah, and maybe that makes sense. Rotating 180 degrees about the origin just makes the x's and y's negative. So those are the same. All right, it is odd, it is not even. So, the topic I want to next introduce is the idea of intervals on which a function is increasing or decreasing. And in order to convince you that you already know this, maybe I'll just take a sample point. At that point on the graph, would you say this function is increasing or decreasing, or neither? I hear a call for increasing. That seems right. As the inputs start going left to right, the outputs will go up. And let's go back as far as we can and still have it be increasing. So how far back could I have this thing go and still have it be increasing? In fact, over that whole stretch, is it? Y values keep going up as the X values go up? So it sure looks like it's increasing. And I'll worry about the endpoints in a moment. On -2 until, when does it stop increasing? About -1. In fact, I've gone a little bit more precise. I've labeled the point on at least my copy as -1.2. But -1 is probably about as good as you could do using the picture provided. From -2 to -1.2, and maybe I'll advertise that that's approximate. So that must mean that it starts decreasing there, right? Decreasing on. So it makes it up to this point and it's increasing there. As soon as you pass x equals -1.2, does it start going, did the y value start going back down? Yeah. How long until they stop going down? Positive 1.2. And you'll know right now that I'm in, well, I'll point this out in a moment. So it looks like it's decreasing from -1.2 until plus 1.2. Does it start increasing again after that?
Yeah.
Nice. And I'll emphasize that I have not indicated any brackets or anything like that. If I were to ask you where this function turns around, what would you tell me?
That's how you get 0, 0.
It's 0, 0. I don't know about that. Like, it seems like it just keeps on going in the same direction, right?
-1.2 and +1.2.
Yeah, it goes from going up and it turns around and starts going down at x equals 1.2. So, I haven't written down any definitions, but we have at least an intuition for what these words should mean. So maybe I'll try to put some formal definitions down. What does it mean for a function to be increasing over an interval I? So, here is a definition I will propose. For all inputs, let's say x0 and x1 in I, if x0 is less than x1, then f of x0 is less than f of x1. So let's just parse this out and see what it says. So I'll say a function is increasing if whenever you take two inputs and one of them is to the right of the other, then the corresponding output will be above the other output. Does that agree with what we've labeled in blue right now? Let's do a quick check of that. So let's take two inputs. There's an x0, there's an x1. So x0 is less than x1. There are the output values. Looking at that graph, is f of x0 less than f of x1? Okay, cool. So it seems to agree with what we need. Using this, let's decide if we should include or exclude the endpoints. So if either x0 or x1 is allowed to be -2, does all that still work? If you take an input in the blue interval that's bigger than -2, is the output bigger than f of -2? Yeah, right, because f of -2 is 0, and any y value otherwise will be bigger than 0. So I think I can include -2. Should I include or exclude 1.2? Now let's think for a moment. So there are no inputs in the interval that are bigger than 1.2, so I don't need to worry about that. If I take an input that's less than 1.2, is the output less than f of 1.2? Yeah.
Is the graph moving at 1.2 or negative 1.2?
Uh,
Or just at a flat stance?
Well, what is that? Making sense of that sentence requires some tools of calculus. Like, what does it mean for the graph to be staying still?
There's no slope or it's, I don't know.
Yeah, so those are great observations, and like formalizing any of those is what calculus does. I agree that like the slope at that point is 0. But if you just take the definition that I wrote, I think that it's increasing over that whole interval. And similarly, it's increasing over that whole interval and decreasing over those intervals. So the definition I've provided will generally have you include endpoints. That being said, on things like tests, I'm not going to get hung up on like the endpoint subtlety. Yeah.
So if they aren't like specific endpoints that you have like dots on, then they're more than likely included.
You mean like if you have a situation like that?
Yeah.
Yeah, I wanted to include that endpoint and include that endpoint. If on the other hand, it did something silly like this,
Then it's excluded.
yeah, then you can't even evaluate that endpoint, so you have to exclude it. Cool. So, what does it mean to be decreasing? Well, the same thing, but inequality switch. For all inputs, x0 and x1 in the interval, if the first is less than the second, then so if you take one input that's less than another input, the function reverses that inequality. That seem like something that agrees with the picture above? Here are two inputs. This one is bigger than that one. Does the function flip that inequality? Yeah, because there's f of the smaller input, there's f of the bigger input. The inequality got flipped. A turning point is a point where the function changes from increasing to decreasing. And let's just see, I know a lot of people who end up taking pre-calc have seen some calculus in the past. If I say the word critical point, maybe people have some memories of that. Cool, those of you who do, that's very closely related to the idea of a turning point. At a place where the function turns around, in some sense, like this definition indicates that it looks like it's both increasing and decreasing. Calculus would say it looks like it's neither. And those are the points that get called critical points. But more on that next semester. So, our remark is that tools from calculus are basically built to find these places where a function turns around. But for now, let's just say this. Apparently, you might go, well, if you want to look at this graph, where are the turning points of this function? What if I wanted more precision? What if I wanted, say, up to the 1,000th place where the turning point is? What would you do? If you're allowed to use absolutely any tool. Yeah.
I think you graph it on your calculator and you look at the table.
Yeah! So, if you pull up a graph, and when you look at this table, like most calculators have like a max function. All that these max functions are doing is saying, well, I've evaluated this sucker at like 10,000 points. Which one gives me a maximum? Or which one gives me a place where it goes from increasing to decreasing? So let's do exactly that. X cubed minus 4x. So, Desmos already will try to find these for me. Oh, that's more digits than I wanted. That is the 1000th place already. Maybe I'm not sure it's rounding correctly then. So if I want more precision, you can get more precision. And on a calculator, you could like zoom in to do that. That feel pretty okay? Oh, God damn it. So if you have a calculator generated graph, you can zoom in. Alternately, you can look at like a table of values the calculator generates. Use that to figure out where the max is. And if you want more precision, just get more precision. There it is up to the 10,000th. Am I counting those digits correctly? Okay, awesome. Cool, people feel okay? Neato. So we have this idea of turning points, intervals of increase and decrease. Here's a related topic. Let's talk about optimization using a graph. And this particular example won't feel motivated at all. If you have a model that predicts something like, I don't know, height, cost to do a thing based on some decisions, you generally are interested in like where it achieves the best possible value. Like what's the maximum you can make for revenue? What's the highest point of all achieves? And you can read this off of a graph. Let's just do that. Here's a graph of a function y equals f of x. What is the maximum value that this function takes? 5. Why 5?
Because it's the largest next value.
I object to one letter in that sentence.
The largest y value.
Or just y value. So let's talk about y. If you want the maximum value of a function, you want... So this is asking what is the greatest output value. And remember, output values, god damn it, I'm off screen. You can stop me when I do that. Sorry, I shouldn't swear that much in class. So, you want what is the greatest output value? Output values on the graph are y values. So when you want to maximize a function, you're interested in what is the greatest y value on the graph. And the greatest y value you see seems to be at this point negative 5, 5. So what's the maximum value this function takes? It takes a max value is 5. So let's jump right down to the third bullet point instead of the second. We'll go back up to that. So what if I asked you for the minimum value this function takes? What would you tell me? I hear a -4. People agree? Yeah, so let's read through it. So the minimum value should be the lowest y value we see on the graph. So let's see. There's y equals -5. I don't see any y values like that on the graph. Yeah, it looks like the first point I hit is at -4. So let's see, both coordinates, 2, -4. Nice. So, the min value is -4. And the color coding that I'm trying to add is just indicating what shows you that on the graph. What if I asked you instead, what is the input that results in a maximum output value for this function? Let's see, the maximum output was 5. What input gives you an output of 5? Yeah. -5. That was a good yawn.
Thank you.
X equals, that pen is dead, -5 results in a max value of y equals plus 5. What input value results in that minimum value?
X equals 2.
X equals 2 because of this. Alright. So I think that tells us enough to say what we mean by a maximum and minimum value. So an input is called a global maximizer if f of c is bigger than or equal to f of x for every input x. F of c is the maximum value. That seem like a reasonable thing to call that? And input is a global maximizer if when you plug in that input, you get something that's at least as big as every other output. That's what that sentence is trying to say. What if I wanted to minimize? How would I change that if I wanted to describe a minimum value?
Sorry.
Yeah.
Okay, so f of c is, and so okay. If f of x is the maximum value,
God damn it. That should be a C.
okay, thanks,
Yeah. So let's read this again and do a quick sanity check. So, what is a global maximizer? A global maximizer is an input that gives you an output that's at least as big as every other. That seem like a sensible thing to call it? So that means the output at C should be at least as big as the output at every other input. Nice. And then we call the corresponding output the max value. What if I wanted to describe a minimizer? Yeah.
Flip it.
Yeah.
Sorry.
By it, you mean like that inequality. And then f of c is the min value. So that's a global phenomenon. To talk about a maximum value, you need to compare this output with absolutely every other output. And something that mathematicians do an awful lot is they say, well, what if I don't care about every other output? What if I just care about what happens nearby? So here's the idea. So I'll describe it in Ward's wider formal definition in a little bit. Let's look for input values that locally maximize the output value f of x. And what does it mean to locally do anything? It means you only look at other values that are close to that value. So let us illustrate by doing this. So what if I were to take that point on the graph and on the dot cams that used to be in this room, like 5 years ago, I could zoom in way closer. I can't now. So this is the best I can do. So if you only saw that tiny piece of the graph, would you say that red dot maximizes? Nope. So this is an example of something that is not a local max. Would you say that if you saw that much of the graph that red dot gives you a minimum value? It is also not a local min. Looking at this graph, let's pick another point. What if I want to zoom in really close on that point? So I only saw the amount of the graph inside of that red circle. Would you say that red dot looks like a local max? Would you say it looks like a local min? Yeah, cool. Here's an example of a local minimum. So x equals 1, 2, 3, -3 is a local minimum. Do you see any others? Are there any other inputs which if you only look close to those inputs, you get a minimum value?
-4.
-4, do? By which you actually mean 2.
Oh, yeah.
Yeah, I want the input.
Sorry.
No, you're good. So is x equals 2. So both of those generate local minima. Let's write down a definition. So a function is called a, well, I guess we just did minimizing, so let's write down a local minimizer. If f of c is less than or equal to f of x for every input x which is close to c. So a function is a local minimizer if it's a minimum value, as long as you only look at other x values that are really, really close to it. And what do I mean by really, really close to? Well, I'm going to be a little bit vague here. I mean as close as you want. Like if you just keep zooming in, it should continue to have this property. How do you think that would change if I wanted to get a local maximizer?
It's like
the opposite.
opposite.
Alright, so let's finish this up by just asking about maximizers. Do you see any local maximizers for this thing? What do you see?
-5.
I'm going to put a star here. X equals -5. Do you see any others?
0, x equals 0.
X equals 0. See any others you'd want to count? Alright. Let me tell you why I don't want to count those. And there is like a subtlety here. So in order to be a local maximum, it must be the case that if you zoom in close enough and compare this output with every other output corresponding to a nearby input, you get an inequality. Can I even compare two outputs that are close to 5 but a little bit bigger than? Nah. So here's the takeaway, endpoints don't count. You have to actually be able to compare it with all of the other inputs nearby. And you can't because the other inputs nearby don't even have outputs. But I'm really glad you said those two because that let me make that point, which is like a really subtle point and a really picky point, but like one that matters. If you're looking for local things, endpoints don't count. Cool. Nice. So, let's carry on and start in on the next thing that I want to do. Ooh, and maybe let's see. So how many people had already started the web walk or open-ended that was theoretically assigned for yesterday? With the ideas that we've now mentioned, do the problems that I asked you to do seem much more reasonable now? Okay. I'm being absolutely atrocious with keeping to my schedule this semester. It's going to be a problem, but it's a me problem, not a you problem. So, yeah, we've got enough time to do this. So we've got some like tools we can do with graphs of functions. We can talk about intervals of monotonicity, you can maximize, you can minimize. Let's start just building some functions whose graphs we just know. And to some extent, this will have to do with a touch of memorization. We'll generate some computer graphs to like get some intuition right now. And then we'll just say, well, now we know what these graphs look like. So let's start with this. Some of these you do just know. What does the graph of y equals x look like?
It's just a straight line of 45 degree angle through the middle.
Straight line, y-intercept is at 0, slope is 1. And you shouldn't let me get away with that. The y-intercept isn't at 0, the y-intercept is at 0, 0. It's a point. What about the graph of x squared? What does that look like? Yeah, see like that hand gesture. And maybe we'll plot a few points. 0 squared is 0, 1 squared is 1, negative 1 squared is also 1, 2 squared is 4, negative 2 squared also 4. Graph of y equals x squared looks something like this. And maybe we'll even pull up a computer-generated graph and compare with some of the rest. Y equals x, y equals x squared, y equals x cubed, y equals x to the 4th. Alright, so that's like a lot of things graphed at once. So the graph is kind of unreadable. Let's introduce them just as we need them. So there's y equals x and y equals x squared. Do those agree with what we just sketched? Awesome. Y equals x cubed. Describe that qualitatively a little bit. Tell me some things about it. To the right of the x-axis, it looks qualitatively kind of like the squaring function. A little bit steep or farther away from the origin, a little bit flatter close to the origin. And it does the opposite for negative numbers instead of the same. What about x to the 4th? How does that compare with x squared?
It's wide.
It's wider close to the origin, and then narrower or farther away. If I narrow for big x values, if I zoom out a lot, then the black curve looks way narrower than the green curve. But if I zoom in real close, the black curve looks wider. Yeah, I like that. And if we want to sketch the graph, well, I guess like it's hard to put in things qualitative like that into a hand-drawn graph. And let's just see if we notice some things. So let's look at these and these pictures and now just like read off some things. Y equals x, even, odd, or neither. Let's see, is y equals x symmetric over the y-axis? No. So it's not even. Is it odd? Yeah, right, because negative x is negative x. X cubed, is that odd? What about these even power functions? As in the power is even. Are they even or odd? These two. Even. Tell me about the intercepts. Where are they? I guess let's do both. Where are the x-intercepts?
X-intercept is at 0.
X-intercept is at, well, I guess 0, 0. Where's the y-intercept?
0,
Also 0, 0, so that's why I just said intercepts. And did it matter which one of these you looked at to get that? Nah. Let's look at those odd power functions. So these two, where are they increasing? Just above 0? Is,
Always increasing.
I think it's always increasing. And let's just check that here. Yeah, it looks like it keeps increasing. It slows down, but it's still increasing. It has that moment of time at x equals 0 where like, if you compute like the slope, you'll get 0, but by our definition, as the x values keep on going left to right, the y values keep going up. Always increasing? Always increasing, Jesus. Never decreasing. What about the even power functions? Where are they increasing?
When x is greater than 0.
When x is greater than 0. I'll be picky and I'll want to include that endpoint, but I'm not going to harp on that. Where is it decreasing? Before x equals 0? And let's just see if that pattern continues to hold. I've like grouped them into even power functions on the right, odd power functions on the left. So let's just pull up a bunch of odd power functions. Are all of those odd? Are they all always increasing? Excuse me, do they all have the same x and y intercepts? Cool. And in fact, qualitatively, they all look kind of like x cubed, right? Like if I just asked you, here's a blank piece of paper, sketch for me very informally the graph of x to the 7th, you'd probably draw something that looks like x cubed. So similar to us doing a lot of walking here. The even power functions all look similar to x squared and have the same like even and odd properties. Feel pretty good? Nice. So here's a pool of functions whose graphs that you should just know. Whenever you see an even power function, you should picture something vaguely like a parabola. It's not technically a parabola, but it's, bowl-shaped at least. Whenever you see an odd power function, you should picture something kind of like x cubed. Let's start building up to the opposites of power functions. Let's talk about OODs. So let's try to sketch the graph of y equals square root of x, not by just knowing what the graph looks like, because we've seen it. Let's do it using ideas. So if I want to take y equals root x and ask you to write x as a function of y, so solve that for x, what would you get?
Y squared equals x.
And I'm going to put a blank here because there's going to be another detail. So let's use that to graph. So that means the same thing as like x equals y squared, but the x's and y's are just swapped. So let's sketch the graph of y equals x squared, but then we'll just swap the x and y values. Doing that. There's the graph of x equals y squared. What would be wrong with saying that's the graph of the square root function?
Square roots can never be negative.
Yeah, so there's one thing. Square roots can never be negative. What's a more philosophical objection you might have? Yeah, it fails the vertical line test. What you said is right too. Both of those are fine responses. So this fails the vertical line test. So how do you fix this? You demand that you only allow for the positive choice of thing whose square is x. So, if you want the graph of y equals root x, 0 is allowed, and then you just copy that down. So there's the graph of the square root function. You exchange the y and x values, and then you make it past the vertical line test. Alright, so in the next, you have the weekend. Have a good weekend. Try to take a look at the remainder of this packet, see what you can do with it. You too. Cool, and as you're on your way out, if you came in late enough that I missed you on attendance, I'd appreciate it if you put yourself out. Oh yeah, go ahead and check. You too. The square means I didn't need it. Just put a check in it.
Yes.
I don't see
Oh yeah, you walked in like not even late, right? You're just at the front, yeah.
I have a question. Are we turning in the packet?
Like this packet?
Yeah.
Nope, that's for you.
Okay.
And if you don't wanna use that, like, you just want to take notes on paper.
No, I don't.
Do it.
I just put it on my schedule yet.
I think enough people take advantage of it, it's
Yeah.
Okay, let's see you stuff you're gonna.
Thank you.
I'm excited about it.
You have no pressure,
Huh?
Bob retiring,
Um,
so you're gonna have, when you hire him,
no,